So we showed how to implement loops in MapReduce and optimize them, and use that to implement the data log pattern language and recursive programs in that language. And we showed different representations of graphs, and now we're going to show PageRank in a couple of different ways at scale. So remember, the context here is that graphs are getting bigger and bigger and bigger. So you can imagine a social scale graph having about 1 billion vertices, one per person, with maybe 100 billion edges. Web scale graph is bigger because there's more web pages than people, so maybe 50 billion vertices and 1 trillion edges. But there's the human connectome, the neural network in your brain, has maybe 100 billion edges and 100 billion vertices and 100 trillion edges. So we need large scale systems to process this, and MapReduce is one such system. There's more coming down the pipe though, so MapReduce is perhaps on the tail end of its utility for these massive scale, but we're going to stick with it for now. So here's an implementation of PageRank in MapReduce. In the map function, we have a node ID and a vertex object. That vertex object has a couple of methods that we use. You can get its current PageRank, in.PageRank, and you can get its adjacency list, in.adjacency list. So in.PageRank divided by the length of the adjacency list gives us the fraction of the rank that we're going to distribute to each of our neighbors across each of our out edges. Then we're going to emit a special key value pair with the node ID and the vertex object, and I'll come back to that in a bit. And then for each of my outgoing neighbors, send the appropriate fraction of my PageRank, which is the value p that we just constructed. Okay, so now on the reduce side, we've got a node ID m and a list of things. Then we initialize a couple of values, this m object to null and a new rank to 0. And then for every p in this list of p's, we're going to check to see if it's a vertex. Now why that's there is if it is a vertex, that means it corresponds to this key value pair that we emitted up there. And all this was a way to pass that complex vertex object through to the reducer. Because remember, the key here is just a node ID. So we need some way of passing this more complex object with some internal structure over to the reduce side. And so now we have it and we assign it to m. If it's not a vertex, then it's one of these other PageRank values that we computed, and therefore we just add it up. And then finally, the new PageRank for that vertex m is going to be this formula that we saw. Well, sorry, I guess I'm being a little glib there. This is the damping factor that we mentioned, and this is a equivalent expression to what we showed before. And finally, now that we've constructed the new PageRank, we emit a key value pair, the node ID and the vertex object itself, which is the same key value types as we need on the map side to repeat this. So we're going to run this over and over and over again with across multiple iterations. So there's some problems with this implementation. The main one is that the entire state of the graph is shuffled on every iteration, right? That little complex vertex object that includes within it the adjacency list associated with that vertex is sent across the network over to the reduce side and handled by the reducer. When all that really needs to be sent is just the new rank contributions, if the vertex state could sort of stay in place. If you could address the neighboring vertices directly and just say, hey, here's your new rank contribution, that would be useful. That would save some communication traffic. Okay. And then also we have to control the iteration outside of MapReduce, including the termination conditions and just the logic itself. So for these reasons, and just to explore another programming model, Pregel was suggested also at Google in 2010. So since then there's been open source implementations, just like there was for MapReduce and Apache Giraffe, Stanford. There's a system called GPS, a system called JPregel, Hama, and this is really designed for batch algorithms on large graphs in particular, so focused on graphs. And so the basic logic looks something like this. It says while any vertex is still active, or the max iterations have not been reached, for each vertex, process all the messages you get from your neighbors, update your own internal state, and then send messages back out to your neighbors. And then maybe set the active flag appropriately. If you don't get any messages, then you're not active. Or if your internal state doesn't change enough, you're not active. And you can control this logic. And so the point is now you're writing, instead of writing a map function and a reduce function, you're essentially writing just one little function, which is the function that I should run on each vertex at every time step. All right, so let's see an example, which is PageRank. Okay, so there's just one method here, compute, and this is this code is a little awkward. This is straight from the Pregel paper. It's a little awkward here because it's in C, so bear with me if you're not used to looking at C. But this says if basically the iteration number is greater than or equal to 1, the super step, then add up all the messages I get from my neighbors, and then assign my own internal state to this new calculation, to the new rank. Then as long as the super step is less than 30, which is our, if we go over 30, we're just going to assume that we've converged and just quit, then send the contribution of my rank to all my neighbors, which is my current value divided by n, and n is just the number of neighbors. Otherwise, set myself to inactive, which is this vote to halt. So you sort of say, I've got no more work to do. I'm done until somebody wakes me up with a new value. Okay. And what's not in here in this implementation, but is often added in a Pregel implementation, is some kind of condition that says, well, if the internal value hasn't changed by a large enough amount, then vote to halt, then set myself to inactive. All right, so let's see how this works, because I'm not sure, the code may or may not be very clear. So imagine we have a graph like this. We initialize the rank to the total number of vertices divided by the number of the number 1 divided by the number of vertices. So there's 5 vertices, so we just divide 1 by 5, which is 0.2. Okay, so that's the initial rank. Then the compute program runs on every vertex simultaneously in parallel, and it sends its rank contribution to all of its neighbors. So this rank contribution of 0.2 divided by 2 outgoing edges, so that each one gets 0.1. And here there's 3 outgoing edges, so each one gets 0.066, and so on. Then on the next super step, all those contributions are added up. And so here we add 0.1 and 0.066, multiply by 0.85, and add in 0.03, because that's our formula, and we get 0.172. And we do the same for all the other nodes. Now, this one's a little funny. Why did this node and this node get 0.03? Well, that's because they have no incoming edges at all, in which case this term in the formula provided nothing. Sum was 0. And so they just get 0.15 divided by 5, 0.03. Okay. And so that's our new value after that iteration. Then it repeats. This rank is divided in half, 0.015 and 0.015. This rank is divided in thirds, 0.01, 0.01, 0.01, and so on. And we see what changes. So we add this up, this plus this times 0.085 plus 0.03 gives us 0.0513, and so on. And then I've marked these vertices as red because their value didn't change from one iteration to the next. And so they're marked as inactive. And that condition actually wasn't in the code that I showed you, but it's typically a condition you add. Okay. And so then the process continues. Here's the new values for the next iteration. We start over again. One optimization here is that these messages aren't actually resent. Again, they can be retained on the receiving side. You know, all the incoming edges have a value, and it doesn't necessarily need to be resent across the network. You can just sit there until it's updated. So if this vertex were active, it would be resent with a new value, but since it's not active, you just use the old value from the previous iteration, and nothing needs to be sent. All right, so we recompute these, but we find out that this top vertex didn't change from one iteration to the other, so it goes red. And then these two values are updated appropriately. And that's our new values for the next iteration. And then finally, remember all the red nodes all the red vertices don't actually get executed at all. And so they don't send any messages and they don't send any messages. Nobody needs them. But this vertex still needs to be updated. And so we apply it again, and then finally the execution halts when all the vertices are inactive. Now, it might take quite a while to converge, in which case, remember, there's that super step less than 30 condition as well. So you don't really need to in general, PageRank starts to get pretty close to converging after some number of iterations. You don't really need to let it run for too long.